Welcome to our differential equations and numerical methods modified COVID-19 model. This model is an SIR with vaccine model. This model is for the spread of COVID-19 and is dependent on the state variables S, I, and R, with the vaccine being administered. Due to time factor, we may not be able to go through the whole code. Nevertheless, the equations used to generate the code is well explained on our website. Now let's get started by exploring how changing some of the set parameters influences our model. A is the infectious coefficient in the week. B is the recovery coefficient in the week. V is the vaccination rate in proportion per week, and so on and so forth with the other set parameters. Now let's see what happens if we drop the vaccination rate from 0.01 to 0.001. We can see that the infectious curve actually gets taller. If we increase the vaccination rate from 0.001 to 0.005, that is about half percent of the population every week. Let's see what happens. The curve actually goes down, which is one of our goals, and it pushes it out in time a little bit, but not too far. Reverting to 0.001, which is about 1% of the population being vaccinated every week, drives the curve back down as we vaccinate more and more people. It does also look like it shifts the graph to the right, but not too far. Let's do 0.02, which is about 2% of the population every week. That will really flatten out the curve. If we give this 2% of vaccination to the population every week, we are actually keeping the infection rate under 20% at all time, which is good in several cases of COVID-19 infection. If we do 0.05%, let's see what happens. We realize that the curve actually gets more flattened, but this is less likely to happen because of the slow vaccines rollout. But if this should happen, we are basically killing out the infectious entirely as everyone recovers and becomes immune. This graph is right because we bypassed going through the infectious pool and we went right from being susceptible to being immune. So that is a great scenario right there if we could do 5% of the population every week. So the solution actually is getting the vaccines out there quickly, which will actually kill the infection entirely, assuming the vaccine has 100% efficacy. Let's say other factors like social distancing comes in and the infection rate actually decreases slightly. We drive the infection peak down and pushes it further out in time, which gives us more time to prepare. If we pushes it down from 0.8 to 0.6, let's see what happens. It actually makes a big difference in the number of people who get infected at any given time. If we buy, as it buys us more time to snatch people from being susceptible right into the recovery pool. Let's say if we go further down to 0.5, what happens? We can just slow it down further, maybe by washing our hands a little bit better, and that actually gets the infectious curve more flattened as people goes from susceptible right into becoming immune. If we can also develop other medicine that can help combat the virus and get people out of the infected pool into the recovered pool faster by increasing the recovery rate B from 0.02 to 0.04, that will really flatten the curve because we are keeping the infected pool smaller. and we can see that here. Oh, there you go. So in conclusion, this gives us hope as we can bypass having to go through infection. So we can really level the infectious curve, which will take the pressure off on hospitals. But the vaccine is the way. That way, we can push infection out in time and keep infectious lower. So a combination of developing medicine and vaccine as lowering the infection rate by our social behavior and other health protocol, all of these can help us to fight the coronavirus and to be able to make it through. Thank you.